Hello, and welcome back. We're still in Chapter 6, dealing with the differential equations. Today we're specifically going to be looking at more separation of variables, as well as a logistic equation. And our objectives are going to be looking at different types of separation of variable problems, as well as looking at homogeneous differential equations, which is a situation where we can't necessarily use separation of variables or not directly. And then we're going to look at application versions of those. So the first thing we're going to look at is separation of variables. Now today we're going to look at the form that can be written in the form of m of x plus n of y dy dx equals 0. What this really is the function of m is going to be in terms of all x's. The function of n is going to be in terms of all y's. And when we have functions written like this, we can still use the separations of variables technique, which we're going to see here in just 1 minute. Example 1 says, find the general solution of, and we have dy dx equals x squared minus 3 divided by 6y squared. Our first step is going to be to isolate all of the y terms with the dy on one side, which I'm going to do on the left, and all of our x terms on the left, or the right side with the dx. So when we do that, we end up with 6y squared dy is equal to x squared minus 3 dx. Now in order to go ahead and finish solving this, we're going to integrate both sides. And when we integrate, the integral of 6y squared is going to give us 2y cubed equals, and the integral of x squared minus 3 will give us 1/3 x cubed minus 3x plus some arbitrary value c. Now to go ahead and solve this separation of variables problem, we want to isolate our variable c. So we get c is equal to 2y cubed minus 1/3 x cubed plus 3x. And if you remember from the last section, we always wanted to clear out any fractions if they existed. And in this case, we have the 1/3 x cubed. So to clear out that fraction, we're going to go ahead and multiply everything by 3. And when we do that, we get 6y cubed minus x cubed plus 9x. And this all equals c. And that completes example 1. Our next example says to find an equation of a graph that passes through the point 1, 1 with the given slope y prime is equal to a negative 9x divided by 16. If you recall, slope, which in this case is y prime, can be written as dy dx. We can say dy dx is equal to a negative 9x divided by 16y. Okay, and from here I see that I can separate and put my x terms with the dx and my y terms with the dy. So I'll multiply both sides by dx and both sides by 16y, and that will give us 16y dy is equal to a negative 9x dx. So if I go ahead and I integrate, both sides. Integrate. I can factor out a 16, and I'm left with the integral of y dy. And I'm going to do the same thing on the other side. I'm going to factor out the negative 9 in this case and integrate just the x dx. And when I do that, I see that I end up with 16 times the integral of y, which is y squared over 2, equals a negative 9, and the integral of x then is going to be x squared divided by 2 plus c. So when I simplify this, 16 divided by 2 is 8y squared is equal to a negative 9 halves x squared plus c. I want to go ahead and get all of my, or I want to just isolate c, I guess you could say. So we could say c is equal to 8y squared minus 9 halves, that's plus 9 halves x squared. And because I'm given an initial value condition this time, you can go ahead and clear out your denominator of the 2 with the x squared, but because I'm given that initial value condition, I can go ahead and just plug everything in as it was. And if you remember, your initial value was the 0.11. And if you recall, to simplify this, all you have to do is plug in that 1 in for your x and y, and then you can solve for your c value. So c is really equal to 8 times 1 squared plus 9 halves times 1 squared, which is going to give you 8 plus 9 halves. Which in this case, if I convert 8 over into halves, I end up with 16 halves plus 9 halves, which is 25 halves. So if I rewrite my equation, I have 8y squared plus 9 halves x squared equals 25 halves. Now, to put it in proper format, I can actually go through and multiply everything by 2 just to clear out those fractions, and I get 16y squared plus 9x squared is equal to 25. And now, this is the equation of a graph that passes through the point 1, 1, given a slope of a negative 9x divided by 16y. Now we're going to look at homogeneous differential equations. What you'll see is some differential equations cannot be solved using a separation of variable technique. And this is true for homogeneous functions. Now, it's said that a function is a homogeneous function of degree n if you can replace your function values x and y with tx and ty, and when you do that, you can factor out t raised to some power, say in this case n, multiplied by your original function. This is said, or you read this as a homogeneous function of degree n, and n is just some integer. And I'll show you what that looks like here. As first example. Now I do want to apologize, when I created the PowerPoint, the function didn't transfer over properly, so it should say f of x equals x squared y minus 4x cubed plus 3x y squared. So we want to take this function and prove that it's a third degree homogeneous function. To do that, we're going to take our function f and evaluate it at tx, ty. So I'm going to go through and replace every x with a tx and every y with a ty. So I end up with tx, that quantity squared, times ty minus 4 times tx, that quantity cubed, plus 3 times tx times ty, and that quantity is squared. So when I go through and I simplify everything, I see for this piece here, my power properties tell me that I have to distribute that 2 onto t and x. So I end up with t squared x squared ty minus 4. I'm going to distribute the 3 onto both the t and the x. So I have t cubed x cubed plus 3tx times t squared y squared. Now I need to go through and combine any like terms. I have a t squared and a t here. So t squared times t is going to give me t cubed x squared y minus 4t cubed x cubed. I can't simplify that term anymore. Plus 3, and I say I have a t and a t squared, which is going to give me t cubed x y squared. Now when I look at this, I notice that every term, in order to simplify, has a t cubed. So I'm going to factor out that t cubed, and I see that I have x squared y minus 4x cubed plus 3xy squared is what's left. Now if you notice, t cubed is being multiplied by your original function, x squared y minus 4x cubed, 3x squared. So I can really rewrite this as t cubed times your original function f of xy. So I just proved that this was a homogeneous function of degree 3. Now let's look at part B, where it says f of x equals, this should be x plus y squared. And we want to prove that this is not a homogeneous function. Okay, so if we start out, we're going to go f of tx, ty, and I want to show you this so that if you run across this scenario, that you know that you didn't necessarily make a mistake, but this does happen. Okay, so when I go through and I replace everything in my function with tx or ty, I end up with tx plus the quantity of ty squared. When we simplify, we get tx plus t squared y squared. Now, with this, you can't write a common t. I see that both terms has a t in it, but it's not the same t. Tx has just one t, to where t squared y squared has a t squared. So because I cannot factor out the same t value, this is not a homogeneous function. Okay, so what that tells me is I can probably maybe try the separation of variables technique. So if my original function, f of x, y, is equal to x plus y squared, I can really go through and say that dy dx is equal to the derivative of that function, since dy dx is a derivative, so the derivative of x with respect to x is 1, plus the derivative of y is going to give me 2y dy dx. So if I combine all my y terms on one side and my x terms, well, we'll get to there in a second. Let's right now move all of our dy dx terms over to the other side. So I'm going to subtract this 2y dy dx here. So I get a negative 2y dy dx plus dy dx equals 1. I'm going to factor out the dy dx. So I end up with 1 minus 2y. That quantity times dy dx equals 1. And then I see that I can easily separate my variables by multiplying by dx. So I really have 1 minus 2y dy is equal to 1 dx. And I can actually go ahead then and integrate and go through and solve for some value of c. If you want to continue on, that's fine. I can double check your work. But for the sake of this example, we're going to be done right now. Next, we're going to look at homogeneous differential equations. And the definition of this is just some equation m dx plus some equation n dy is equal to 0. The key piece is that both functions m and n are of the same degree. So if we look at example 5 says that we just have to prove that this is a homogeneous function of degree 2. Again, to prove that we have a homogeneous function, we have to prove that we can go in and replace our x's with tx and our y's with ty's and get a common t term out. So this is really x squared plus xy, and that's a quantity times dx, plus y squared dy is equal to 0. So let's go ahead and replace all of our x's with tx. So I get tx squared plus tx times ty, this is all times dx, plus ty, that quantity squared, dy, and this is all set equal to 0. So when I simplify, I have t squared x squared plus tx ty, all of that's times dx, plus t squared y squared dy. Now if I go through and I combine my like terms, I see that I have t squared x squared plus, I have a t times a t, which is t squared x y dx, plus t squared y squared dy. Now, if you look, I see I have a t squared here and a t squared here, which tells me I can factor a t squared out, and I'm left with x squared plus xy times dx, plus I have another t squared here, so I have t squared times y squared dy. And this means now that I can factor out a t squared out of my entire function. So when I do that, I have t squared times my function of x squared plus xy dx plus y squared dy. And because I was able to factor out this t squared here out of everything, that verifies that I have a homogeneous function of degree 2. Now for part B, we're going to verify that this x squared plus 1 dx plus y squared dy equals 0 is not a homogeneous differential equation. So if we go through and replace our x's with tx's and our y's with ty's, we will see that we get tx squared plus 1, and all of this is multiplied by dx, plus ty squared dy equals 0. So let's go ahead and simplify. That means we get t squared x squared plus 1 dx plus t squared y squared dy equals 0. Now, I can't go through and, well, I can factor out a t squared from this equation, and I can factor out a t squared from this part, but this term here that deals with the 1 does not have a t squared in it. So because that does not have a t squared in it, I cannot factor a t squared out of this whole piece here. Therefore, because I cannot factor out a common t term, this is not a homogeneous differential equation. Okay, now we can actually solve homogeneous differential equations by the method of separation of variables. The only thing is we have to use a change of variables to do that. So theorem 6.2, which is the change of variables homogeneous equations theorem, says that if we take some function m dx plus some function n dy, and if this is a homogeneous function, then we can actually use the separation of variables technique by substituting y equals v of x into the equation. V is just a function of x. So if we look at example 6 says find the general solution of the quantity of x squared minus y squared dx plus 3xy dy equals 0. So the first thing we're going to do is we were told that y equals vx. So wherever I have a y in this original equation, so like this spot right here and this spot right here, I'm going to plug in that vx. But I also have this little guy right here, this dy. So that really means the derivative of y. So if I go ahead and I solve for dy from this y equals vx equation, I know that the derivative of a product, because this is v times x, is equal to the first, which is v, times the derivative of the second, or dx, plus the second, which is x, times the derivative of the first, or dv. So now I know I can substitute vx in for every y, and for dy, I'm going to plug in this v dx plus x dv. So let's go ahead and do that here. So we end up with x squared minus y squared, which is now going to become vx squared, and all of this is times dx, plus 3x, my y is going to become vx, and my dy is v dx plus x dv. Let's go ahead and simplify. For our dx term, we have x squared minus v squared x squared times dx, plus this here is going to become 3x squared v times v dx plus x dv. And again, now if I go ahead and distribute this term onto both this term and this term, I see that I have x squared minus v squared x squared times dx, plus this will give me 3x squared v squared dx plus 3x cubed v dv. Now, I see that I have a dx term here and a dx term here. Let's go ahead and combine those. That gives me x squared minus v squared x squared plus 3x squared v squared, and these are all our dx terms, plus 3x cubed v dv. Now from here, I can go ahead and simplify my negative v squared x squared term with my positive 3x squared v squared. So I have x squared plus 2x squared v squared, and these are our dx terms, plus 3 x cubed v dv. And these are all equal to 0. We should probably keep that as a part of our equation. Now the next thing I'm going to do is I'm going to go through and I notice I have dv terms, or dx terms here, and dv terms here, and it's being set equal to 0. So what that means is I can get all of my dx terms on one side and all my dv terms on the other. So to do that, I'm going to have x squared plus 2x squared v squared, and these are our dx terms, and I'm going to set that equal to a negative 3x squared v. Now, if you notice, every term here has an x squared, so let's factor that out as well. So we have x squared times 1 plus 2v squared dx equals x squared times, oops, and this up here is really an x cubed, a negative 3x v dv. So now I'm going to divide everything by x squared just to get rid of it. I end up with 1 plus 2v squared dx is equal to a negative 3xv dv. And I actually have my dx's and dv's already separated. Now I can go ahead and get rid of or isolate my x terms on one side and my v terms on the other. So I see that I can move this term, because it has my v stuff in it, over to this side here with this dv, and if I divide by an x here, I can have my x over on this side here with the dx. So let's go ahead and do that. So that's going to give me 1 over x dx equals a negative 3v divided by 1 plus 2v squared dv. Now we have a separation of variables problem. And oops, let me get my pen turned on. Now we can go ahead and integrate it. So let's integrate both sides. I know that the integral of 1 divided by x is really the natural log of the absolute value of x. And I'm going to factor out the negative 3. So I have a negative 3 integral of v divided by 1 plus 2v squared dv. Now off to the side here, I'm going to say u is equal to 1 plus 2v squared, which means du is going to be 4v. I see I only have a v up in my numerator here, so that means I'm going to have to multiply my dv, oops, I'm sorry, this is dv, by 4, which means I have to divide out front by a positive 4. So that's really going to give me a negative 3/4 times the integral of 1 over u, which in that case is a natural log situation as well. So this gives me then that the natural log of the absolute value of x is equal to a negative 3/4 times the natural log of the absolute value of u, which we identified up here as 1 plus 2v squared plus c. Because we're taking the natural log of everything else, we can go ahead and take the natural log of c as well, because it's some constant. So now we know that we want to get rid of any fractions, and to do that we will multiply everything by 4. So that's going to give us 4 times the natural log of the absolute value of x is equal to a negative 3 times the natural log of the absolute value of 1 plus 2v squared plus properties of exponents, we know that a 4 in the front of a natural log is really going to become an exponent. So I have natural log of x to the 4th is equal to. Now this plus sign means a product with natural logs, and this coefficient of a -3 also means an exponent. So what that gives me is the natural log of c times the quantity of 1 plus 2v squared raised to the power of -3. Now, we know that in order to cancel out a natural log, I can e both sides, and an e raised to the power of a natural log is going to cancel. So now we're left with x to the 4th is equal to c times the quantity of 1 plus 2v squared raised to the -3rd power. Now I'm going to go back and use that, or use the fact that y was equal to vx, solve that equation for v, so v is equal to y divided by x, and I'm going to plug that in now for every v. So that gives me x to the 4th is equal to c times the quantity of 1 plus 2 times y divided by x raised to the 2nd power, and I'm going to raise all that to the -3rd. So I get x to the 4th is equal to c times the quantity of 1 plus 2y squared divided by x squared, and that whole quantity is raised to the -3rd. My final step then is going to be to get c by itself, since that is our goal, and I see that c is equal to this, if you recall, and maybe I should have written this over here, that something raised to the -3rd power is really, all that means is it needs to go in the denominator. So this over here was really c divided by the quantity of 1 plus 2y squared divided by x squared. So in order to clear out that denominator, I really have to multiply the other side, which is x to the 4th, by that denominator. So I end up with c is equal to x to the 4th times a quantity of 1 plus 2y squared divided by x squared, and then we're done. Now we're on to the application. The first example that we're going to look at is example 7 dealing with wildlife population. Okay, this example says the rate of change of the number of coyotes in a population is directly proportional to 650 minus nt, where t is the time in years. When t equals 0, the population is 300, and when t equals 2, the population has increased to 500. We want to find the population when t is equal to 3. Well, when you see that key phrase there that says that the rate of change is directly proportional to, you should think back to section 6.2, where we could rewrite dn dt as a proportional function, which was k times whatever we're proportional to. And in this case, it's that 650 minus n of t. If we use our separation of variables technique, we see that we have dn is equal to k times 650 minus n of t dt, and I want to isolate all my n terms on one side, all my t terms on the other. So in order to do that, I'm going to have to divide by this 650 minus n of t. So I have 1 over 650 minus n of t dn is equal to k dt. Oh, sorry. So in order to solve, I'm going to integrate. And when we integrate, both sides. I have a 1 over situation, and it looks like I can call u 650 minus n of t, which means du is equal to a negative 1. So I really end up with the integral, and I'm going to factor that negative out, of 1 over u du. So this is going to give me a negative natural log of the absolute value of 650 minus n is equal to, and the integral of k dt is just kt plus c. So now if I take and get rid of that, first of all, let's get rid of the negative. So if I divide both sides by negative, I have the natural log of the absolute value of 650 minus n equals a negative kt minus c. And we know that to cancel out a negative log, that we can e both sides. So these are going to cancel out, and we're left with 650 minus n equals e to the negative kt. Hopefully, from our previous sections, you remember that when we integrate and do this kind of stuff, that we also now have to include our constant in here with this e, and that's c. So if I solve for n, I now see that I have, let me change colors here, n is equal to a positive 650 minus ce to the negative kt. Now we're given that the initial value, or when time t equals 0, the population was 300. So let's just write t equals 0. Our population, or n, was equal to 300. So from that, I can go ahead and solve for my c value. So I have 300 is equal to 650 minus ce to the negative k. I still know what k is, but I know t is 0. That's going to make this whole piece here equal to 1. So c is going to be equal to 650, or I'm sorry, 650 minus the 300, which is going to give us 50. So now my equation becomes n, or the population, is equal to 650 minus 350 e to the negative kt. I can go ahead and solve for my k value by using the second scenario that was given to us. And that second scenario was when t equals, I believe it was 2, our population n was equal to 500. So using those numbers, I end up with 500 equals 650 minus 350 e to the negative k times t, which is 2. I'm going to subtract my 650, which is going to give me a negative 150, equals a negative 350 e to the negative 2k. I'm going to divide by a negative 350. So when I divide by a negative 350, I see that I have 3/7 is equal to e to the negative 2k. If I take the natural log of both sides, so the natural log and the natural log, these are going to cancel. And I have the natural log then of 3/7 equals a negative 2k. So k then is going to equal the natural log of 3/7 divided by a negative 2 I do have that as approximately equal to 0.4236. However, I would suggest that you store that value into your calculator. So now I'm going to get down to the initial the initial problem, which said find the population when t equals 3. So if I want to find what my total population when t equals 3, I can use my equation that n is equal to 650 minus 350 e to the negative, and I'm just going to plug in that 0.4236, but I would use that saved value into your calculator times a t of 3. And when I did this, I got a value of something around 552 coyotes. Alright, and I apologize, I actually did all the work on the other slide's problem. But the one thing I do want to point out is if you graph this, you see that you get, when you graph this, you'll see that you end up with a function that looks something like this curve. And what you also notice is that it says when n is equal to 650, you get some type of a horizontal asymptote, okay? Now with population growth, realistically, we know that it doesn't grow to infinity or exponentially, okay? There's some type of a leveling out, okay? And that leveling out or that horizontal asymptote on a graph is what we call our carrying capacity. The final thing we're going to look at in this section is called Logistic Differential Equations. We know that the exponential growth model was actually derived from the fact that a rate of change of variable y is proportional to the value of y. And from the last couple of sections, we looked at the derivative of y with respect to t in a proportional equation is ky has a general solution of y equals ce to the power of kt. Now, we've also discussed the fact that even though exponential growth is unlimited, when we're dealing with populations, we have an upper limit called a carrying capacity that we don't exceed as time increases. And this type of growth, which is logistic growth, can be actually modeled by the equation dy dt equals ky times a quantity of 1 minus y divided by L. Now, we know that K and L are both positive constants, and your L value has to deal with the population or your carrying capacity. And what we can see, and I'll show you this here graphically in a second, but if y is some value between 0 and your carrying capacity, then your derivative is greater than 0, or in this case positive, so that's telling us that our population is increasing. If we were to go and we were to solve this logistic differential equation for y, and you can do this on your own if you like, you would find that you get your that y is equal to your carrying capacity L divided by 1 plus be to the negative kt. And then to go back to what we were talking about here a second ago, if your y value is less than L or less than your carrying capacity, then your derivative is less than 0, which tells us that our population is decreasing. So here is a curve, and you can see where it kind of plateaus out or approaches your carrying capacity L. Now, for our final example, and I'll have to give you this equation. I apologize it didn't transfer over when I did the Dropbox. But our final example says, the State Game Commission releases 100 deer into a game reserve. During the first 5 years, the population increased to 432 deer. The growth rate of the deer population is given to us as dp dt, and let me write this down below. So dp dt is equal to kp times a quantity of 1 minus p over 100. And during the first 5 years, the population, so the commission believes the population can be modeled by a logistic growth model with a limit of 2,000 deer. we want to write a logistic growth model to show that the population size, or to show what the population size over the next 30 years is going to be. So going back to the equation that we just solved, which was the y equals L divided by 1 plus BE to the negative KT. Okay, this is going to be our general model that we want to find. We can plug in information based on this original equation that was given. We know L is our carrying capacity, and the carrying capacity then is going to be our limit, which was given to us in this original problem up here, and the original limit was 2,000. So I know that L is equal to 2,000. So I can then go ahead and replace our L. I'm looking for population P. I can replace my L with 2,000 divided by 1 plus BE to the negative KT. Now I'm going to have to use those initial conditions that were given to me in order to find my B, my K, and then eventually my population after 30 years. So to do that, let's go ahead and use our initial condition that was given. And that initial condition was that our population at time 0 was equal to 100, because we released 100 deer initially. So I'm going to go ahead and plug in 100 is equal to 2,000 divided by 1 plus BE to the negative K, and I know that my time is 0. Because I have 0 times the negative K, anything raised to the power of 0, this is going to give me 1. So now I have 100 is equal to 2,000 divided by 1 plus B. Well, in order to solve for B, I can multiply both sides by 1 plus B, divide by 100, and this is going to give me 1 plus B is equal to 2,000 divided by 100, or 1 plus B is equal to 20, so B then is equal to 19. With that piece of information, I now have an equation that looks like P equals 2,000 divided by 1 plus 19e to the negative kt. So if I want to go in and solve for my k value, I'm going to use the second piece of information that they gave us, which was P of 5 years. It was equal to 432 deer. So now if I go in and I plug everything in, I have 432 deer are equal to 2,000 divided by 1 plus 19e to the negative k times my t, which is 5. When I multiply both sides by the 1 plus 19e to the negative 5k and divide by 432, I get 1 plus 19e to the negative 5k equals 2,000 divided by 432. So to solve for k now, I'm going to have to subtract 1 and divide by 19 to get e by itself. So I have e to the negative 5k equals 2,000 divided by 432 minus 1, and that quantity divided by 19. This is, oh, well, I guess we'll do that here in the next step. So if I continue on, I'm going to natural log both sides. So let me change my pen color. So if I take the natural log of both sides, I now have a negative 5K is equal to all of this stuff. So if I take that stuff and divide by a -5, I highly suggest that you store that, because that's quite a lot to keep typing in every time. I get a K value that's approximately equal to 0.33106. So now that I have that number, I have a population model that looks like P equals 2,000 divided by 1 plus 19e to the negative 0.33106, and again I would use your exact value, times t. So if I want to go in and evaluate my population, so right here's the actual model. If I want to evaluate my model after 30 years, I'm just going to go in and plug a 30 in for that t, and I find that P of 30 then is equal to 1,998 deer. So I see that I'm really close to approaching that.